Hello, in this video we go over section 2.1, the distance formula and the midpoint formula. Okay, so let's begin with the distance formula. This formula right here is to find the distance between 2 points, P1 and P2, and it's denoted dP1, P2. So essentially what we do is, in the Cartesian plane, given some point P1 and another point P2, measure that distance between the 2 points. Alright, so let's do an example to find the distance between the points 1 and 2, 1 comma 2 and 5 comma 5. So in this case it would be a good idea to label this as our x1, y1, x2 and y2. This would help us with where to find, or rather to substitute, the numbers in the formula. So let's write down the solution. So in this case, d equals to the square root of x2 minus x1, which in this case it's going to be x2 minus x1, 5 minus 1, quantity squared, plus y2 minus y1, which in this case is 5 minus 2, quantity squared. And all we do from here is simplify this expression. Again, keep in mind the PEMDAS order of operations. Whatever it's in the parentheses goes first. So 5 minus 1 is going to be 4, plus 5 minus 2, which is 3. Now we evaluate the squares. That's going to give us the square root of 16 plus 3 squared, which is 9, which will give us the number 25. But in this case, this is a nice number which we can simplify a bit further, because we know that the square root of the number 25 is 5. And we'll write just units because they're not specifying whether these are centimeters, inches, kilometers, etc. Okay, so for example, if this were the point 1 comma 2, and it looks like, visually speaking, and this other point were the 5 comma 5, the distance right here from P1 to P2 would be 5 units. That's the visual for this type of exercises. Let's do another example. So in this case, let's label this again. This is x1, y1, x2, y2. So d equals the square root of, again, let's refer to the formula, x2 minus x1, which in this case is 1 minus negative 2. Okay, 1 minus, be careful here, negative 2 squared, plus y2 minus negative 1, quantity squared, in this case y2, which is negative 4, minus y1, which is 3. So in this case, you might want to be very careful with the signs. Okay, so here again, keep in mind that you can use the smile rule here. So that's going to be 1 plus 2, quantity squared, plus negative 4 minus 3. That's going to give us negative 7 squared, which in this case this will be 3 squared plus, again, negative 7 squared. That's going to give us a 49. We can evaluate that one. Alright, and 3 squared, that's going to give us 9 plus 49. If we add these two numbers together, what are we going to get? So 49 plus 9, that's going to give us 58. The square root of 58 rather, right? That's the operation inside of the radical. So in this case we are going to try and find a way to factor this out. Okay, so let's see if we can divide the number 58 by a perfect square, in this case by 4. But in this case it's not going to work. 58 divided by 9 doesn't work either. 58 divided by 16. So it's not going to work in this case to simplify this radical any further. So let's just call it units as well. Okay, you don't have to write this units word when you're doing the homework on MyMathLab. It's just a number. I'm doing it here just to give a little bit of context to the problem that we are working on. Okay, so the next piece of information that we are going to do is the midpoint formula. So if we have the points on the Cartesian plane, point P1 and point P2, doing these operations here, using these formulas, it's going to give us the point that lies exactly in the middle. Okay, so this is P1, this is P2, this is going to be M, the point that lies exactly in between the two given points. So let's do one example. Let's do a couple of examples. So find the midpoint between the points 1, 2, and 5, 5. Okay, so let's see. Let me write in this case the formula M, which is the sum of the x's divided by 2, comma, the sum of the y's divided by 2. In other words, all you're doing is finding the average between each of the coordinates. That's going to give us the midpoint. Okay, so in this case, x1, x2. So x1, which is 1, x2, which is 5. That's going to give us, oops, not x anymore. So that's going to give us 1 plus 5 divided by 2, y1 plus y2, which in this case this is y1 and this is y2. 2 plus 5 divided by 2. Okay, so 1 plus 5, which is 6, divided by 2, which can be reduced. 2 plus 5, which is 7, divided by 2, cannot be reduced. Again, keep in mind to reduce everything that you can. So in this case, 6 divided by 2 is 3, comma 7 halves. So that's the point that lies exactly in the middle between 1, comma 2 and 5, comma 5. Let's do another example. So in this case, well, I already have the formula here. I'm not going to write it again. So M equals x1 plus x2, which in this case negative 2 plus 1, and 3 plus negative 4 divided by 2. So in this case, negative 2 plus 1, that's going to give us a negative 1 half, comma 3 plus negative 4, that's the same as subtracting 3 minus 4, that's also a negative 1 half, which is the midpoint, the point that lies exactly in between these two given points. A very classical problem in college algebra is the following. Alright, so we are given 3 points. Okay, 3 points in which, number one, they ask us to plot them on the Cartesian plane that we have in there, right? Which is what I'm going to do now. Okay, so I'm going to plot the point A, which is negative 2 comma 1, the point B, which is 2 comma 3, and the third point C, which is 3 comma 1. Okay, so let's form the triangle ABC. Okay, so that's gonna give us that's what we're gonna get when we draw this triangle. Okay, part B. Well, actually, first of all, let's call this point A, point B, and point C. Find the length of each side of the triangle. So in this case, we are going to have the segment AB. We're going to have the segment AC and the segment BC. Okay, so we are going to have 3 segments. Okay, so we are going to find the distance between the 3 points. So the distance from A to B, I'm going to call it like this. I'm going to use this notation this time. So from A to B, we are going to have x2 from B minus x1 from A, which in this case is 2 minus negative 2. Be careful here. Quantity squared plus y2 minus y1 in this case. 3 minus 1, quantity squared. So in this case, you might want to use the smile rule here. Minus minus turns into a plus. So 2 plus 2, that's going to give us 4 squared. 3 minus 1, 2 squared. Alright. And then, simplifying this, we're going to get 16 plus 4, which is going to be the square root of 20. But this number can be simplified a bit further because this number 20 has a perfect square as a factor inside of the radical. So so there's a few ways to factor out the number 20. 10 times 2, but none of the factors there are perfect squared. Another way is 5 times 4, in which 4 is one of the perfect squares. Alright, so I'm going to highlight the number that is a perfect square, and I'm going to take the square root of that number, or rather I'm going to use the property of radicals. When we have the radical of a product of 2 numbers or more, we can write that as the product of 2 radicals. Okay, that's something we learn in intermediate algebra. And in this case, we evaluate the one that has the perfect square. So 2 square root of 5. So there goes the first one. There goes the first one. Now let's find the distance between B and C, between this point B and this point, that point C. So the distance will be 3 minus 2, which is x2 minus x1, 3 minus 2, quantity square plus y1 minus y2 minus y1, which in this case is 1 minus 3, quantity squared. And in this case, if we simplify 3 minus 2, that's going to give us a 1. And 1 minus 3, that's going to give us negative 2 squared, which will result in 1 squared, which is 1, plus 2 squared, which is 4, everything inside of the radical, which equals the square root of 5. So there goes the second distance, okay, the distance BC. Okay, it would be great if we write them down. So I'm going to use orange. In this case, this will be 2 square root of 5. This is going to be square root of 5. All right. And let's do it the last one, AC. This will be the square root of x2, which is 3 minus x1. Okay, so which in this case is 3 minus negative 2. Careful with the signs here. Plus y2 minus y1, which in this case is 1 minus 1 quantity squared. But hey, look at that. That's going to be 0. 0 squared, that's ultimately going to be 0. And you might want to use the smile rule here. So 3 plus 2 squared plus 0 squared. But 0 squared is nothing other than 0. And in this case, 3 plus 2, that's 5. And then if we square the number 5, we get 25, which is a nice number 5, which is this length from A to C. And actually, you can see it in the grid. How many units? 1, 2, 3, 4, 5. This one is easy to see, but not the other ones, because these are weird numbers. So at least you can sort of see that everything we're doing is consistent. Okay, so let's put check marks to part A, part B. Okay, verify that the triangle is a right triangle. And in this case, when they ask this question, it doesn't mean by just looking at the triangle, because, well, if you look at this, indeed, this is a right triangle, because the segments AB and BC form a 90-degree angle, but that's not how we are going to show. Okay, so everything here is part A. This is part B. Let's do part C. How are we going to show that algebraically? Well, you might remember a very powerful theorem relating the lengths of the sides of a triangle, in particular at a right triangle. That is called, yes indeed, the Pythagorean theorem, in which it states that the square of the sum of the squares of the quantities of the lengths that form the right angle is equal to the square of the hypotenuse. In this case, well, due to the perspective of the paper, if you prefer, let me put it like this. Okay, this could be A, B, and C. So for our purpose, if we try and do this, right? So this is going to be our AB squared plus BC squared equals AC squared. So that's going to be the sum of the squares of the sides equals the length of the hypotenuse squared. Okay, so let me put the back again to its original position. So I'm going to do that. Okay, so it must be true that AB squared plus BC squared equals AC squared. So let me use a different color to write that. It must be true that this condition is met. Okay, so what is the length of the side AB? From the picture, we know that it is 2 times the square root of 5. Okay, so 2 times the square root of 5, quantity squared, plus the quantity BC, which is the square root of 5, equals the length AC squared, which is 5. Okay, and that quantity squared. Alright, so how are we going to simplify this? Well, here the radical cancels the square, which is going to give us a 5 here. And here, if you prefer, you might want to distribute the power to each of the factors. What am I doing here essentially? What am I doing here essentially is AB to the n power equals A to the n, B to the n. So in a way, it's like distributing the power to every single factor inside of the radicals. Alright, so this is going to be 2 squared times the square root of 5 squared. Okay, and 5 squared equals 25. So what is 2 squared? 2 squared equals 4. And in this case, there's a radical cancels the square, and that's going to be times 5 plus 5. Is that equal to 25? Well, let's find out. 4 times 5, that's 20. Adding these two numbers, we get 25, which the condition is met. We must have that both sides are the same. Okay? So let's put a check mark for part C. Now let's do part D. Find the area of the rectangle, of the triangle rather, not the rectangle. All right, how are we going to do that? Letter D. It is very important here to recall the formula to find the area of a right triangle, which in this case area equals 1/2 the base times the height. Okay, in this case, under this perspective, this because it's a horizontal line, looks like a base, all right? However, it is not the base. We need to go back and twist the page here to the correct perspective so we can see the two sides that form the right triangle. This guy right here is, okay, I'm running out of colors here. Let me use red. This is the base, and this is the height. Okay, so base times height times 1/2, that's going to give us the area of that right triangle. Okay, let's see. So the base which is 2 times the square root of 5 times the height, which is the square root of 5. So the 2's cancel and we get square root of 5 times itself is the square root of 5, 180 squared. However, keep in mind that the radical with the square cancel, giving us an area of 5, in this case, units squared. Okay, 5 squared units. And this is the end of this exercise. So let's put a check on letter D. There's one more here. There's one more. Another classical problem. Alright, find all points having a y coordinate of 6 whose distance from the point 1, 2 is 17. Okay, what is this problem about? How about we first draw a picture rather than me just showing you the formula and doing a lot of calculation without even knowing what the hell we're doing. Alright, so let's see. So let me draw a Cartesian plane. And I'm going to locate the point 1, comma 2, which is going to be roughly here. Okay, so the key part here is this: all points having a y coordinate of 6, whose distance from that given point, which is the point 1, comma 2, is 17. Alright, now, so we are going to move 17 units in certain direction. It doesn't have to be perfect. It's just an estimation. So 17 units in a way that we get to the point x, comma 6. This point right there, right here. But also by symmetry we can get another. Let me call this x1 and let me call it x2, or x1 and x2, it doesn't matter, comma 6. So we are going to find those 2 points, the values of x of these points, whose distance equals 17. This will require to solve a quadratic equation in a combination with radical equations, you will see. So first of all, let's recall the distance formula. So the distance formula, x2 minus x1 squared plus y2 minus y1, okay? So, in this case, we don't know one of the values. Which one is it? Okay, we know the distance. The distance is 17. Okay, and x2 minus x1, which in this case this is going to be simply, let me just call it x. Well, x2. Let me just call it x2 because that's the one I use for this label. Okay, ultimately we are going to come up with 2 separate answers, so I will change this symbol in the next step. Minus x1, which is 1, quantity squared, plus y2, which is 6, and then minus 2, quantity squared. So let me just call it x right away, okay, just so we don't get confused with the other values. So I'm just going to erase this subscript right here. Alright, so our goal is to solve for this x, for this variable x. In this case we cannot just move it to the other side. We have this square, we have all this here. So this is what I'm going to do. First I'm going to simplify a little bit here. 6 minus 2, which is 4 squared, and then x minus 1 quantity squared. Everything inside of the radical. At the same time, what I'm doing is reversing the sides of the equation. Again, keep in mind that you can always write equation, for example, equation 3x plus 5 equals 9. It's the same as 9 equals 3x plus 5. Either way, it doesn't change. But the reason why I am reversing the order of the sides is because I'd rather have the variable in the left hand side of the equation. Okay, so I'm going to start solving this equation. The first thing that I'm worried about is this huge radical. So in this case, we are going to do the opposite of taking the square root, which in this case is to square both sides. So in this case, cancel the radical with the square, x minus 1 squared plus 4 squared, which equals 16, equals 17 squared, which equals 289. Now, I know what you're thinking about this equation, maybe FOIL this or expand the binomial squared. However, it may not be necessary because we would need to use the quadratic formula to solve that equation. And if you look at the form of this equation, it is already in the form for what is this called, for the square root property. Okay, it's already good for that. So I'm going to subtract 16 to both sides. Notice in this case, just so you know, this is going to give us like really weird numbers. Okay, so don't be scared. So this is going to give us 273. All right. The next step would be to take the square root in order to get rid of this square. However, is it possible to evaluate the square root of 73? Let's see. Second square root of 273. Okay, well, number one is going to be a really wacky number, and we don't want decimals. So when you do the homework, you don't want decimals either. So I'm going to start dividing the number 273 by the possible perfect squares. So I'm going to divide by 4. Of course, it's not going to work. 273, divide that by 9. That's not going to work either. And what about what's the next one? 16 to 73. No, it's not going to work. 3 divided by 16 to 73 divided by 25 is clearly not going to work. And so nope, nothing is going to work here. 36, 49, let me see if 49 works. Nope, we can 49, that's not going to go. So we're going to leave it like this, 273. Okay, so in this case, take the square root on both sides. And this is going to give us x minus 1 equals, by the way, don't forget the plus minus for the right hand side, plus or minus the square root of 273. Solving for x for this equation, all we need to do is add 1 to both sides, and we get the following. X equals 1 plus or minus the square root of 273, which in this case we're going to get two x's. x1, which is 1 minus the square root of 273, and x2, 1 plus the square root of 273. Alright? Okay, so this is the solution to the equation. Now they're asking us for the points that have a y equals coordinate 6, whose distance from the point 1, 2 equals 17. So in this case, the points are P1, 1 minus the square root of 273, comma 6, and P2, 1 plus the square root of 273, okay, comma 6. Those are the points. And this concludes this section. See you in the next video.